Hello. Hi, Jennifer.
Hi, am I it?
Hey, how are you doing?
I'm good. How are you?
I'm well, thanks.
So is it just me and you?
Well, no, I think, let's see, I see another person. Let's see, Felicia. Let me, so there, that makes three. Hi, Felicia. So, Jennifer, since you were the first person here, I'll start with you. Do you have any questions that you'd like to look at?
Really all of them.
Okay, well, pick one and let's start with that, and then we'll just see what other people ask about and how much time we have.
Okay, on section 8.2, question 2.
Number 2. Okay, I've got a book here. Let me look and see. 8.2. Can you read me the problem?
Oh my God.
The hard copy that I have is the 6th edition, so I always like to make sure that we're on the same page. Okay. Sometimes they change them just slightly, and so if you'll just tell me what your version says.
It's the one about credit card debt. It's been reported that the average credit card debt for college seniors is $3,262. The student senate at a large university feels that their seniors have a debt much less than this, so it conducts a study of 50 randomly selected seniors and finds that the average debt is $2,995 and the population standard deviation is $1,100.
Okay.
And okay, I'm getting on my, whatever this little sign is, the
Alpha.
omega.
That's
alpha.
Omega.
My glasses. Anyway, is 0.05. Is this student senate correct?
Yeah. Okay. Great. So I think that none of the numbers had changed in my edition, so we're all on the same page. So, what are your thoughts on how to get started here? What might you do first?
I'm going to be completely honest. I have no idea.
Okay.
This is the hardest thing I have ever done. So.
Well, you know what, I will say that hypothesis testing usually is the culmination of most introductory statistics courses, and so it is, can be a challenge because it basically you're having to use everything that you've learned so far.
Yeah.
So this is we are asked to conduct basically a hypothesis test on behalf of, what are they saying, the student senate. So I think if we're going to do a hypothesis test, the first thing that we should do is to clarify what the two opposing hypotheses are. So one of those we're going to call a null hypothesis, and then there'll be the flip side, which is usually called the alternative hypothesis. And so we need to be clear on what those two opposing opinions are, because that's what we're testing. We're going to find evidence in favor of one, or maybe it supports the other. So let's just be clear on what the two viewpoints are here. So when it says, is the student senate correct? Can you tell me correct about what? What are they, what's their hypothesis, or what are they curious about?
Okay. I feel just stupid. They're curious if they'll have less debt. Is that right?
Exactly. Yeah, right. So I want to see for now. This is students at this particular large university. So I'm going to just say our students have less credit card debt. Okay, so I'm going to write something on here. If you can look here, and I want to just show you the symbols that I'm using. So I know that I'm going to need two hypotheses, the null and the alternative. And so I'm not trying to use symbols just I'm writing the theory that we're testing is that our students at this college have less credit card debt. Now, less than what?
Okay, less than the average of the 3262, correct?
Yes.
Yay.
I'm going to write this also just in words first. So you are right. So for me, I just wrote right now, just to kind of get things sorted out in my mind, the null hypothesis, which is always, the null hypothesis is always that there's no change. It's the status quo. Whereas the alternative is just like the name implies, it's an alternative to that. So the null hypothesis here is the students at our university have exactly the same credit card debt as everybody else. We're no different. The alternative is that we differ in some way. Now, sometimes that's saying a less than, sometimes it's more than, or sometimes it just simply does not equal. So now I want to go a step further, and I want to translate what we've just written into mathematical or symbolic form. So I'm going to, below this, I'm just going to rewrite the symbols that I use for the null and our alternative. And I'm going to just fill in some specific values. So let me share with you what I wrote first. So the null hypothesis is that the average at our school is the same as everywhere else, specifically 3262. So that's the Greek letter mu. And so I'm saying that the null hypothesis is that our average is the same as everybody else's average. So that's what we said in words up here. You know, the ours is no different. We have the same average credit card debt. Now, the alternative theory is that ours is actually less than the national average. So let's see if we can translate that into a symbolic statement. So in symbolic form, I'm saying that the alternative hypothesis is that the mean, that's the Greek letter mu, is less than, so our average is less than the national average, is basically what we're saying here. So here I just kind of wrote out in English what we're trying, what's under debate. And now I'm just translating that to the mathematical symbols and the specific values. In a hypothesis test, we're usually either going to be testing theories about the mean, or sometimes it's about a proportion. And in this case, we're testing whether the mean is in our local environment is the same as it is in the bigger world, or if it differs in some ways, in this case, less than. Okay, so let's see. Here's the two, that's the first step in conducting a hypothesis test. It's just being clear about what the two opposing hypotheses are. I think we're good to go on that next step. To move on to the next step. Now, I usually would tell my students at this point once we have the clear statements about our hypothesis, we kind of have to look at like what the evidence that's available. So I'm going to just write a statement here that says gather evidence. Now, in this case, let me say what that evidence is. The evidence that we've collected, well, we didn't have to actually collect it, but the evidence that the state senate or the school senate, whatever it was, that they collected, is that they took a random sample. And so I wrote here, this is the count. There, this n equals 50. And the result from that random sample is that they had a sample mean. So I'm using the symbol X bar. The sample mean was 2,995. So this is the evidence that we're using to test these theories. Okay, so let's look to see, think about what the distribution of X bar would be. So X bar is a sample mean, and we have a sample size of 50. So do you know what we would call what we expect the sampling distribution to look like? Does that question make sense to you? Okay, so you know, as long as either your population is normal, or if you have a sufficient sample size, when you take repeated samples, we expect the distribution of X bar, the sample mean, to be normal. In other words, bell-shaped. And so, as soon as I know that something has a normal distribution, there are two pieces of information that I immediately ask for. I want to know where that is centered, in other words, the mean, and then how spread out it is, the standard deviation. So we already know that in a hypothesis test, I want to point out something. The assumed truth going into this is the null hypothesis, that the mean is 3262. So that's the prevailing sentiment, is that the mean. So when I look at, come down here and I'm thinking, you know, what does this distribution of X bar look like? I'm thinking, where's the center? The assumption is that that's going to be centered at 3262. And the second piece of information we need is the standard deviation, and that was given to us
1100, yeah.
As 1100. So the sampling distribution for sample means is going to be approximately normal, centered at 3262 with the standard deviation of 1100. I'm going to just, for me, it's helpful to have a picture here. And you know what? I actually just misspoke. I've left off a very important step, but luckily we caught it early. When we're talking about this sampling distribution, remember it's sigma over square root of n. And so that's not a straight up 1100. It's actually 1100 divided by the square root of 50, which is approximately 155.56. I'm going to just make that little correction there. And now I want to add a few more details here. So I drew a picture here for us. And so you can see I have a bell-shaped curve because it's normal. Now, on the bottom, I've listed, standard values. These are like correspond to z-scores. So zeros in the middle. There's -1, +1, -2. And so I just wrote in a few of the key z-scores. Now, in our particular distribution, the center actually corresponds to this mean. That's the 3,262. So in this particular distribution, that's the center. Now, if you standardize it and convert it to a z-score, that value is going to correspond to 0. So the values on the bottom are standard scores or z-scores, but in this particular distribution, 3262 is the center, and each standard deviation is approximately $155.56. Okay, now, that's the assumed distribution based on the null hypothesis. Now, we went, and remember we had this evidence that we've gathered from our 50 participants, and in that group, the average was $29.95. Now, let's look at where this value, $29.95, fits into this picture. So in order to do that, I'm going to label a couple of more of these values. So let's say I have 3262 minus 100. Give me just 1 second to make a few calculations here. Okay, let me kind of just bring you up to speed with what I was doing. So in my picture, I said that the center of this distribution is 3262. Now, if I subtract one standard error, remember, this 1,100 divided by the square root of 50, this is our standard error, $155.56. If you subtract 155.56 from this amount, that gives you this guy. What was it? It's backwards to me, but 31. Yeah, 06, yeah. If you subtract the same amount, 155.56, you do it one more time, you get the value that corresponds to -2 standard deviations. And so that's the 2950.88. Now, in the sample that we took of 50 students, we had a result of 2995. Now, the reason that I labeled this is I want you to see that 2995 falls somewhere in between these two values. In fact, draw a line somewhat arbitrarily. You see, I just kind of put it in the picture there. This really dark line corresponds to 2995. Now, notice that's a little bit more than 2950, but a little bit less than 3106. So somewhere in between here and here. Now, how do I convert that? I know that z-score is going to be somewhere between -1 and -2. But I want to find it exactly. How do I convert that value to a z-score? Do you know the formula for that? It's okay if you don't.
No, I'm telling you, this is a completely foreign language to me.
Okay, well, I can. Okay, so let me just write it down here. So in order to convert this to a z-score, we use that formula x bar minus mu. And then in the denominator, that's a sigma over square root of n. The sigma over square root of n, that's the same value that we just calculated right here, 1,100 over the square root of 50. So this is the number that's going to be in the denominator. Roughly, it's 155.56. The mu that's in this formula is this guy, the 3262. And the X bar is our sample result, the 29.95. So you can see I'm going to take a minute and look at this calculation right here. So we've got, and let's go ahead and do this calculation so that we have a z-score. And let's round at 2 decimal places. Do either of you have a result?
Negative 1.72.
Excellent, excellent. So great. Now, does that kind of agree with our picture? Let's look at it again. I said it was going to be somewhere between -1 and -2. Now, if we had made any kind of calculation error, for instance, if you had told me the answer was positive, I'd be like, that doesn't make any sense. I know that the answer should be negative. And even more than that, I know that it should be between -1 and -2. So I think it makes perfect sense that we get a z-score of -1.72. Now, what I'm going to do is look up the probability associated with that z-score. So let's go to table E in the back of your book and find the z-score -1.72. And when you have a result, let me know.
.0427.
Yes. Now keep in mind the way that your table is set up. Table E always gives you area to the left. Now, in this particular test, when you go back to our original symbolic statement here, our theory was that the mean was less than 3262. The fact that this is a less than statement lets me know I'm conducting a left-tailed test. So I'm looking for the probability in the left tail, on the left-hand side. So basically, I'm looking for the area under the curve that's to the left of that. Well, that's exactly the way table E is set up. Table E always gives you area to the left, and that's perfect for this example. And so the value that you found of 0.0427, that represents this area that I've darkened here. It's the area under the standard normal curve that's to the left of a z-score of -1.72. And you can always think of this as being either area or probability. So that basically means, let's think about what we have here. The assumption based on the null hypothesis is that the mean was 3262. Now, we said, okay, we're going to give you the benefit of the doubt. That's the assumed middle. You'll notice that's what we use in the middle of our drawing here. Now, we have a theory, though, that it's less. So we went out and gathered some evidence. Now, in the sample, we got a result of 29.95. So what we're asking is, what's the likelihood, if this is true, that the mean is 3262, what's the likelihood that we would get this result when we went and sampled students? Well, the likelihood of getting a result of 29.95 or something more extreme, there's about a 4% chance of that happening. That's what this means. But even if this is true, if this is really where the center is, the likelihood that we would get a result over here is just about 4%. Now, you have to ask yourself, when there's a 4% chance of something happening, do you consider that rare or exceptional, or to you, is that kind of run-of-the-mill and expected?
I would consider it rare. A 4%
Yeah, it is
chance
rare.
would be rare.
When something is rare, it seems to contradict our initial assumption. When the result that we get is an unlikely result, it seems to say, yeah, you know what, I'm not buying our original assumption. Now, the original assumption that I'm talking about in this case was that null hypothesis. So our result seems pretty unusual when we try to say that this is the center of the distribution. So it seems to contradict the null hypothesis. Now, I asked you just intuitively if you thought 4% was rare. Now, everybody's going to have different definitions of what they consider to be rare or unusual. But we have one more piece of information that we haven't used in this problem. This guy.
Yeah.
So the alpha is your definition of rare for that problem. Now, so the alpha here was 0.05. So I prefer to just speak in percentages. Alpha is 5%. Now, the probability that we got was 4%.
Right.
So since our probability was actually less than the threshold of alpha, so 4% is less than 5%, what that tells me is that I'm not buying this. The original assumption is like, I give you the benefit of the doubt, I'm going to work on that assumption, but I've actually seemed to find some contradictory information. So I'm going to just draw a big old X through the original null hypothesis and say, you know what, I tried, but it just doesn't work. So what that says to me is I'm going to reject the null hypothesis because my evidence, my sample result is just really unusual in my opinion. And so I'm going to make a decision that in this case, since my p-value is less than alpha, in this case, 4% is less than 5%. So I reject the null hypothesis. I'm just going to show you my notes here. The p-value, the p-value, that was the 4%. So, you know, again, I'm just kind of, it was 0.0427, but I'm just speaking in percentages. That p-value was less than my level of significance. That's the alpha value. So since my 4% is less than 5%, which was my kind of cutoff, so that says, you know what, I reject the null hypothesis. And so going back over here, that's why I just marked that out and said, nope, I don't think that's true. So reject the null hypothesis. So what does that mean? If I reject the null hypothesis, it seems to say there is evidence sufficient evidence that the average credit card debt at this university is less than the national average. So if that would be my statement to kind of summarize the results here. So we have evidence, sufficient evidence. And what were we trying to test? Remember, so the actual, working theory here, going back here, our original thing is that our student credit card debt is less. You know, that our students have less credit card debt. Well, we found evidence that that's true. So we rejected that it's the same as the national average, and our evidence supports the claim that our student debt is less. And so that's the whole process. So going back through here, the first thing that we did was really just be clear about what it is that we are testing. So just be clear on what your two hypotheses are. That was the very first thing that we did. And then kind of look at the evidence that you've gathered. So there were 50 students, they had a sample mean of this amount. Think about what you expect the distribution to look like. That's what we did here. And where this sample result falls in this distribution. And if that seems to be, if you get a result that's close to the middle, then that's certainly not going to be contradictory evidence. That would seem to support that this is the true mean. It's when you get results out in either tail that it becomes, that the evidence kind of shifts in favor of an alternative. Now, we actually were able to quantify this probability using the table E. And so that's how we came up with 4%. And then I compared that to the level of significance, alpha. If the p-value is less than your level of significance, you're going to reject the null hypothesis. And that seems to provide evidence in favor of the alternative. It's a process. So, it's not, you don't just look at this and know the answer. I mean, you've got to kind of work
right.
It helps me to be very systematic or methodical about it. And so I kind of have a process, and I do every one of them the same way. And I draw pictures. I try to use illustrations to keep me straight. But why don't we do another one? And let's kind of, I want to, I'll provide a framework, but I want you guys to kind of fill in more of the pieces. And so what's the next problem from this section that is part of your homework?
Number 4.
Number 4? Okay. So remember, the first thing to do, to read over the problem and think about what are the two hypotheses here. And let's just, you don't have to worry about writing this in math symbols. You can just make a statement in English about what do you think are the two opposing viewpoints. What are the theories that we're testing here?
The null hypothesis would be the average salary of $12,837. And then the dean of a graduate study at a large university feels that PhD students earn more than this. The studies show 44 randomly selected students, their average was 14,445.
You know what? So that is different in mine. So you, yeah, I don't have. It doesn't look like I have a similar problem. So, would you mind to read it to me one more time?
Full-time PhD students receive an average salary of $12,837, according to the U.S. Department of Education.
Mm-hmm.
The dean of graduate studies at a large state university feels that PhD students in his state earn more than this. He surveys 44 randomly selected students and finds their average salary to be $14,445. And the population standard deviation is 1,500 with a alpha of 0.05. Is the dean correct?
Gotcha. Okay. All right. So, and Felicia, you may have already answered this. So what do you think is the alternative hypothesis here that we're testing?
That PhD students earn more than the 12,837.
Exactly. Our PhD students earn more. So and so if that's the alternative, is that they earn more, what would be the null hypothesis?
That they earn an average of 12,837?
Yeah, Yeah, perfect. Yeah. So the null hypothesis, remember, once again, is that there is no difference. So that our PhD students earn just what everybody else does. It's no different from the larger population. And the alternative here in this case is that it's more. Now, can you write that using mathematical symbols? So we'll have
Okay. Less than.
so let me know when you have had time to do that.
All right.
Okay. So I'll just give you a minute here and let's look at this together. So the null hypothesis, so that's an H with a little subscript of a 0 there. And then I use a colon, is that mu, the average is 12,837. But the dean or whoever it was has a theory that it's actually more than 12,837. I want to point out, when you're writing these two hypotheses, the values are always going to be the same. You know, it either is this amount or it's different in some way. And so here the null is that it is 12,837, and the alternative is that it's more than 12,837. Okay. Now let's look at the dean's evidence. So there are two things that we're looking for in particular: a sample size and then a sample mean. So what was the sample size here?
44.
Yep. And what was the sample average?
14,445.
Yes. Now, the next thing I want you to consider for me is the distribution, the sampling distribution of the sample mean in this scenario. Now, once again, we have a pretty large sample size of 44. So that tells me that my sampling distribution is going to be normal. And so I went ahead and I wrote a statement here that my sampling mean follows this normal distribution. And now there are two pieces of information that I want. Where is it going to be centered, and what's the standard error? So this center of distribution is the hypothetical, the value from our null hypothesis, so the 12,837. And the standard error is going to be sigma over square root of n. Now, you see that we have the sigma in this case. That was the population standard deviation, which was 1,500. And